All right, hello and welcome to the first session on the last day of crypto on fully homomorphic encryption. As a reward for making it to the morning session on the last day, I have chocolates for everyone. So if you would like one, please come up at the end of the session to the front of the stairs here. And I'm, as I guessed, I think I do have enough for everyone. So thank you for coming. Our first talk is going to be exploring the advantages and challenges of Fermat in TT in FHE acceleration, and Aita will give the talk.
Hi, my name is Ekta, and I'm a PhD student at Graz University of Technology. And this work focuses on hardware acceleration of homomorphic encryption. This is a joint work done by researchers from Samsung and Graz University of Technology, and was funded by Samsung and Zukunftsfonds Steiermark, Austria. Since this is the first talk of this track, I will give a brief introduction to fully homomorphic encryption. As most of us know, fully homomorphic encryption allows computation on encrypted data. It enables secure processing of sensitive data in untrusted environments. So if you are a client and you have some private information that you want some prediction, for example, done by an untrusted server, you can homomorphically encrypt your data, send it to the server, which you do not trust, and the server will still be able to perform a prediction evaluation and send you the result, which only you can see. So in this entire process, the privacy of users' data is preserved. And this is the beauty of homomorphic encryption. The idea of privacy homomorphisms was introduced in 1978, and in 2009, we had our first fully homomorphic encryption scheme. And since then, there have been a lot of homomorphic encryption schemes proposed in literature. The state-of-the-art ones being based on lattice-based constructions, to offer very good performance. And even after decades of these research, decades of these schemes being proposed, fully homomorphic encryption schemes continue to be computationally intensive. And the gap compared to plain computation is quite large. They are 10,000 to 100,000 times more or less performant compared to computation on plain text data. And this is what motivates us to explore hardware acceleration of these schemes to bridge this gap. And there have been several works in literature that attest to this, that try to bridge this gap in terms of hardware acceleration. One such work is the state-of-the-art work done from our lab itself, which is bridging this gap by around 3,000 to 6,000 times. However, there is still a long way to go. And with this work, we realized that there is a certain plateau that these works are reaching. And communication bandwidth, for example, plays a significant role in inhibiting this performance advantage, inhibiting us to achieve more acceleration. And therefore, we wanted to explore what are the challenges from the very root and see if we can fix them at that level itself before going into design level. And this brings me to the acceleration challenges that we face while implementing homomorphic encryption in hardware. The most important challenge is that we have to deal with a lot of polynomial arithmetic operations. These can be addition, multiplication, subtraction, or rotations. And each of these polynomials have a large degree, and the coefficients in these polynomials are also quite huge. So to put things into perspective, if we compare, for example, with the recent NIST standardized PQC schemes, Kyber, dilithium, you will find them somewhere very close to the origin across number of coefficients and size of coefficients, as they have around 256 coefficients in a polynomial, and each coefficient is around 12 to 23-bit large. And now if we take a look at the parameters that are required for a homomorphic encryption scheme, we will see that the bottom three blue dots that you see that can support linear regression, function approximation, or logistic regression only allow level computation. They cannot support bootstrapping in schemes, for example, CKKS. And yet, they require already 16,000 coefficients, and each coefficient is around 1,600 bits large. Then if we go to the parameters which can evaluate certain neural networks and support bootstrapping, an important operation that allows homomorphic encryption schemes to become fully homomorphic, then at this stage, at these parameter level, we are already dealing with 65,000 coefficients per polynomial, and each coefficient is around 1,800 bit large. The modern CPU architectures that we currently use are all 64-bit, And we have to deal with 1600 to 1800 bit large coefficients per polynomial. And this is a very, very significant data blow-up. Because of this data blow-up, we have ciphertext, which occupy megabytes of storage, and evaluation keys used for key switching, for example, that occupy gigabytes of storage. And most of the accelerators that we focus on, hardware accelerators, are either utilize FPGA platforms or chips. And FPGAs and even chips have a certain on-chip memory limit. We simply cannot store gigabytes of data on these chips, and therefore we rely on very expensive off-chip to on-chip communication. And this communication is a bottleneck when it comes to FPGA acceleration because we can compute a lot faster, but the to and fro data offload and onload is what inhibits this acceleration to go beyond a certain point. So now these polynomial arithmetic operations are handled in hardware using number theoretic transform. So number theoretic transform enables polynomial multiplication, which would naively take order of n square, to be computed with a complexity of order of n log n. So to be computed with order of n log n. And how this number theoretic transform works is, if you have to multiply two polynomials, let's say a and b, then first we transform them to entity domain using the entity transformation, which has the complexity of order of n log n. And in this entity domain, the multiplication becomes linear order complex, so order of n. And then once you have done this multiplication, you can transform it back to the polynomial domain. And each entity here looks something like this. So I'll give you a very simple explanation. We pass pair of coefficients through something known as a butterfly operation. And in this butterfly operation, as you see here, for example, x0, x2 will be multiplied with the root of unity omega. And this multiplication is very expensive. For example, each coefficient was around 1800 bit large, and so is omega here. And we are performing this huge multiplication, which will be done pairwise on all n coefficients log of n times. So this is very expensive operation done on very, very large coefficients, 1600 bit coefficients. And to relieve this or to relax this, for modern architectures, not just in hardware but also in software, residue number system is used, where the big Q, the 1600-bit modulus, is broken down into multiple smaller moduli in the RNA space, and then we process these coefficients, smaller coefficients, one by one. For example, if we start with 1600-bit initial modulus, we break it down into 64-bit or 54-bit moduli, multiple moduli. So this gives us a lot of polynomials, but each polynomial has smaller coefficients. However, now, earlier I only needed one entity for the big modulus Q, but now I need one entity that can support all of these moduli. So I need now data path and control path flexibility to support all the bases in this RNS, to support all the moduli in the RNS space. And if you take a look at the area consumption of the prior state-of-the-art works, we will see that this entity unit continues to consume the most amount of area across all hardware accelerators in terms of compute units. It consumes around 80 to 90% area when compared to other units, for example, random number generator or automorphism or multiply and accumulate unit. This particular unit is one of the most area consuming unit. And improving this unit is the direction of this work. So in this work, we explore if we can make this entity unit, which consumes such large and huge number of multipliers, very inexpensive. Can we completely remove the multiplication and just use simple shift operations? Can we use one common entity that can be used across all moduli without having to need data path and control path flexibility? And with this goal, we propose a format number-based technique where we use format number as an auxiliary modulus. So before performing entity conversion, we propose switching the modulus from the RNS basis to one common format modulus. So initially, we were doing the switch to entity before polynomial multiplication. So polynomial multiplication can be done faster. Now we will do a switch to format number base. And what is evident here is that since all the bases are transforming to one common format number, I do not need a data path flexibility in my entity. I can use the same entity for all the bases. Another very important advantage of using Fermat number is, for Fermat numbers, the roots of unity is a power of 2. So the omega that I was multiplying will still be very large, 64-bit, 1600-bit, but it is a power of 2. So I do not need a multiplier to multiply it. I can do a simple shift operation. And so my entity transformation is very, very inexpensive. I do not need a single multiplication in the entire entity transformation. Another important advantage is that storing so many twiddle factors, so these roots of unity, we refer to them as twiddle factors. And for each RNS base, storing so many twiddle factors almost occupies storage equivalent to 1 polynomial per base. And since this is a power of 2, we don't really need to store it. We can have a simple counter to maintain the offset. And so we also save a lot of storage requirement when it comes to these twiddle factors or roots of unities. However, this all is not good yet, because this has a very big caveat. And the problem here is that we need a very large Fermat number to support such operation. This is because for this Fermat number of the form 2 raised to power k plus 1, we can only get k power of 2 twiddle factors. And with this, we can only perform a k by 2 point negacyclic entity. And so when my polynomial degree is 2 raised to power 16, I need a Fermat number which is around 65,000 bit. So I'm now going back to the problem that I started with, where we had very large coefficients. And now we are again back to the same problem with this auxiliary modulus switch. So I am now dealing with 1,200 times larger coefficient, which is quite huge and quite going in the reverse direction from where we started. So to solve this problem, we propose using a simple univariate to multivariate switch. What this enables is that you do not have to use such a large Fermat number. You can use a smaller Fermat number, do smaller entities, but multiple smaller entities. So this will give you a multivariate switch. And here, instead of directly doing entity on the initial polynomial P, initial polynomial modulus of Fermat number, we will now do a switch to the multivariate, and then we will do multiple smaller entities. So for example, when I had my polynomial degree of 2 raised to power 16, we will use a Fermat number which is just 128 bits. And now we will, since we can only do k by 2 point negacyclic entity, we will split the ring into multiple smaller rings like this. So we have to go through 2 levels of decomposition to obtain 3 smaller entity groups that we can operate entity on. And because we can only do k by 2 point negacyclic entity, but we have to do it on a ring of size k, every level of decomposition adds 2 times more coefficients. So since we did 2 times more decomposition, the number of coefficients increase here by 4 times post this technique. So for example, so we take a toy example of 32 coefficients and a Fermat number which is 16-bit. Here again, we'll have a 3-level decomposition. And to accommodate the 4 times increase in the size, we will do a 0 padding in the beginning. And the data, 32 coefficients, are stored across 2 sheets and 4 cross-4 rows and column. And first we start with a row-wise entity. Then we do a sheet-wise entity, which is much smaller. And then we do a simple transpose operation and perform again a row-wise entity. And you can see here we do not need a long 32-bit entity at once. We're able, the largest entity that we have to do is 8-point entity. And the coefficient size only increased to, for example, 16-bit in this case. So overall, we do see a coefficient size increase. We do see the number of coefficient increase. However, this increase is much, much less compared to the original proposal of simply using a Fermat number. So we bring it down to 8 times increase only. And at this point, we felt that it is ready to take it to the design level and see what trade-offs do we face in implementing this Fermat number-based entity. So any typical FHE accelerator has 3 important components. The entity inverse entity unit, as I mentioned, is the most important area and performance-hungry component. Then we have the multiply and accumulate unit, which is used for polynomial multiplications, additions, and the automorphism or conjugation unit. And here, when implementing, we face a very important communication versus computation trade-off, because now we have 8 times more data to handle. So in the prior accelerators, there was no difference between the size of polynomial in simple polynomial domain or in entity domain. The sizes were the same. And so all the prior works were storing data in entity form in the memory itself. So they would load data directly in the entity form, process it on the chip, and then send the data back in entity form. There is no need to convert back and forth. However, if now we use the same technique and load and store data in the MB entity form, we have 8 times more data. So we need 8 times higher bandwidth, and this will, in a way, cancel out the advantage that we get in terms of area by using a cheap multiplier-less entity. So what we do here is we respect the communication bottleneck, and we propose loading data in polynomial form itself, so we don't have to require more bandwidth or have to offer slower performance because of the bandwidth. And then we propose that we should do entity and inverse entity on the fly on the chip. So every time data is loaded, it is converted to entity form. The computations requested are performed upon it, and then it is converted back to inverse entity form, where it is again smaller and sent back to the memory. So with this, in order to deliver proper performance for this architecture, we require a lot of entity units. So typically accelerators have 1 or 2 entity units. We require 4 such entity units to offer comparable performance. Then we have a pseudo-random number generation unit to generate the public component, or the A component of the key switching keys on the fly. Then we have 2 automorphism units, 2 MAC units modulus the format number, and 2 MAC units modulus the RNS spaces, and 4 lift units to transform from the RNS basis to the format base and back and forth. So these are all the compute units we have in our hardware. Then we have an on-chip memory, which acts as a buffer to store initial, final, and intermediate results. And this chip communicates with the off-chip memory via this. So we have a high bandwidth memory directly communicating with the chip. And then we have a program control that communicates with the CPU or the software to load more data onto the HBM, for example. And if we look at the area consumption here, then one such MBNTT that we propose consumes almost half the area for the same configuration as our previous work read. So we get a significant advantage in terms of area for one entity, but the fact that we require so many more entities to deliver the same performance sort of cancels out this advantage. And with this area consumption of 28 nanometer ASIC technology running at 1.2 gigahertz, we get 1,200 times speed up compared to software evaluations. And this brings me to the future scope of this work, which is the limitations first. So we faced this problem that we had to require 4 times more entity because of the communication overhead. And we feel that in architectures where communication is not such a big problem, for example, processing in memory, where data resides very close to the computation unit, this proposal can find very good hope in such architectures. And the second problem was that we still needed a lot of arithmetic operations to do this univariate to multivariate switch, for example. And there are techniques in literature, for example, the Schonage-Strassen or Nussbaumer's approach that can help alleviate the number of arithmetic operations that are needed to perform these conversions. So if you have some ideas on this, please feel free to get in touch, and we are very willing to collaborate and take this idea further beyond this paper. Thanks for your attention, and please feel free to ask questions.
Are there any questions from the audience? I have a question. So in the course of arriving at this idea of the Fermat number approach, were there other things you tried before that didn't work out?
Initially, we started with Fermat number because I think in zero-knowledge proofs, for example, this kind of a technique is used to use power of 2. And this was not extended to homomorphic encryption, so we thought of using the same technique. But then we faced this modulus problem that I mentioned, so we had to find a solution for it. Yeah, but this is how we started initially, so we didn't go in a lot of other directions.
Thank you. Let's thank our speaker again. All right, our next talk of the session is going to be on the practical CPAD security of exact and threshold FHE schemes and libraries, and Marina will give the talk.
Yes, so hi everyone, I'm Marina, and so thank you for the nice introduction. I'm going to talk about the practical CPAD security of exact and threshold FHE schemes and library. So it's a joint work with Renaud Sirdet, Elmen Budwiga, and Jean-Paul Bultet. So here's a quick overview of my talk, and let's start and talk about FHE. So as you now all know, FHE, homomorphic encryption, is a cool corpus of cryptographic techniques to perform meaningful calculations directly over ciphertext. So here we've got a message M, which is transformed by function F, and we actually need this transformation to be carried out on ciphertext. And that's exactly what the magic eval operator does. It transforms an encryption of M into an encryption of its image by F. So eval may be implemented simply through homomorphic additions and multiplications. And currently, FHE security relies on LWE. So a message is encrypted through noisy linear equations in a secret vector S. Noise is required, because otherwise, an attacker can simply pick encryptions of 0, get a linear system, solve it, and retrieve the secret key. So the bottom line is no noise, no security. But, well, there's a problem. Because in FHE, noise magnitude increases with each homomorphic operation. And if it grows too much, this may lead to incorrect decryptions. Bad news for correct calculations, and also bad news for security, as I will show it in a moment. But right before, a word about security context. So all used FHE schemes are proven secure against CPA adversaries who have only access to an encryption oracle. And all are easily broken by a CCA1 adversary, so do not speak even about CCA2 because of malleability. So FHE is at risk as soon as an attacker is granted access to a decryption oracle. But what if this decryption oracle is a very limited one? This is what occurred in CPAD security, introduced in 2021 by Lee and Michencio to model passive adversaries against FHE. CPAD can be seen either as a restriction of CPA or as an extension of CCA security. So we'll just first look at the second part. Right before, here we have this hooded lady. We'll call her Eve. She will be our adversary. So in CPAD, Eve still has access to an encryption oracle, but also to an evaluation oracle and to a decryption oracle. She cannot ask the decryption of a ciphertext that she would have modified on her own, because the decryption oracle doesn't take ciphertext as input, but indices into a game state, and this game state is only populated by calls to the encryption or to the evaluation oracle. Said differently, the decryption oracle only accepts well-formed ciphertext that are either fresh encryptions or encryptions homomorphically derived. It's a hard word, you should try. Homomorphically derived from fresh encryptions. And consequently, CPAD does not capture any CCA aspect. So at the other end, how far it is from CPA? Well, at first glance, not that far. This limited decryption oracle shouldn't give Eve any advantage because, say, if she chooses M, she chooses F, well, she can simply compute F of M. And more generally, she can compute every output of the decryption oracle. So CPAD seems to collapse into CPA security. You see me coming? There's a flow. Well, indeed, in 2021, Lee and Michencio proved that this intuition was erroneous for the CKKS approximate scheme. Just a word, in CKKS, a message M is encrypted by computing M minus AS plus E, and the decryption is achieved by removing the AS term, returning m plus e. But look, the decryption does not return exactly m. And in fact, it leaks the error supposed to ensure the scheme's security. And in this scheme, an adversary who has access to a decryption oracle just can recover ciphertext noises, get a linear system with the secret key as the only unknown, and then recover this key, which is bad, bad, bad. So there remains a question. It was unsettled to know whether exact, with quotes, exact schemes were subject to such kind of CPAD attacks. And because such schemes like BFE, BGV, or TFHE perform some form of error correction upon decryption via rounding, the FHE community assumed that they were just not subject to CPAD attack. Well, too good to be true, as I will now present you a key recovery attack that succeeds on all of the schemes and almost all the libraries that implement them. So the principle of the attack is quite simple. An adversary can gain an advantage when the adversary has access to when incorrect decryptions may occur. And do you recall that in full homomorphic encryption, noise increase with each homomorphic operation? Well, the attacker uses this flow to trigger incorrect decryptions. So the LWE noise is what prevents us from finding the secret key. And the first idea Eve has is to remove this noise, or rather, to find enough noiseless ciphertext to directly get linear equations in the secret key. The issue is that Eve does not know which ciphertext happen to have a zero noise, so how can she identify them? Well, quite simply. First, she asks the encryption oracle for an encryption C0 of 0 with unknown noise E. And then she asks the evaluation oracle to add this encryption to itself, getting a new encryption of 0, C1, with noise 2E. So yes, we all agree 0 plus 0 equals 0. But meanwhile, Eve has doubled the noise. And repeating k times this yields to an encryption CK, an encryption of 0, with noise 2 to the power of KE. And the decryption oracle accepts to decrypt it because it only results from legit homomorphic additions on well-formed encryptions of 0. The trick is that when 2 to the power of k is greater or equal to q over 2t, where q and t are the ciphertext and plaintext moduli, then that encryption of 0 erroneously decrypts to 1, unless, of course, the noise was equal to 0 from the beginning. So Eve has a way to identify noiseless ciphertext. And the key question is whether noiseless ciphertexts occur frequently enough to mount a practical attack. And the answer is, unfortunately, yes. In fact, with usual BFV parameters, where variances are very small and ciphertext moduli very large, noiseless ciphertexts occur with a probability greater than 1%, which is already enough to mount a practical attack that succeeds in less than a day. But for TFHE, this probability is much smaller, but still non-negligible in the security parameter lambda. So the attack still works, though it will take more time. But I will now show that we can do much better. Starting from an encryption of 0 with unknown noise E, we wish to generate two encryptions of 0 with noises alpha star E and alpha star plus 1 E, which will respectively decrypt correct. Oh, okay, I have it. So I'll do again with noise alpha star E and alpha star plus 1 E, which will respectively decrypt correctly to 0 and erroneously to 1. When we have that, we can conclude that the absolute value of the noise is bounded as follows, and so it's uniquely determined and coincides with the floor of the right-hand bound as soon as this quantity equals the ceiling of the left-hand bound. So the question is, again, whether this occurs frequently enough. And the answer is, again, yes. In fact, we've shown that this occurs as soon as the absolute value of the noise is strictly less than the square root of q over 2t, which is almost always the case for BFE-style parameters and happen with an above 20% probability for TFE-style parameters. But there remains a crucial question. How do we generate ciphertext with noise alpha e for an arbitrary alpha using only CPAD game requests? Well, do you recall the CK ciphertext from previously with noise to the power of KE? We can simply sum the CK ciphertext provided that 2 to the power of k appears in the binary decomposition of alpha, and then determine alpha star with a dichotomic search. Are we done? Well, almost. We just got the absolute value of the noise, and we now need to sort the ciphertext according to their noise signs. So let's consider two ciphertexts with large noise alpha e and alpha prime e prime, such that the sum of their absolute value is greater or equal to q over 2t. The trick is to simply add homomorphically these two ciphertexts, getting a new ciphertext with noise alpha e plus alpha prime e prime that will correctly decrypt to 0 if e prime and e have different size, because the sum remains below q over 2t, and will erroneously decrypt to 1 otherwise. And so we have identified a set of ciphertexts with the same unknown noise sign. And we only are left to solve two linear systems, one for each sign hypothesis, getting two candidates' value for the secret key. And we can determine which one is the correct one by simply asking for a few more encryptions of 0, trying to decrypt them. The correct one will always output 0. And once we have the correct key, we just trivially win the CPAD game. So we've tested and implemented our attack on several open source libraries, among the most widely used in FHE. And we've showed that it was not just theoretical, but effective and easy to set up, taking an average of 1 hour to run on a standard laptop. There are various optimizations to this attack, but even in its basic form, is completely practical. Just a word about the runtimes. The runtime primarily depends on N and to a lesser extent on Q, and that's why the attack is exceptionally fast for TFHE. Now, a setting that is particularly subject to CPAD is the multi-party threshold FHE setting. In threshold, we have multiple users, and each user possesses her own public-private key pair. And the users create a joint public key, which they all possess, and which is associated with a joint secret key split among them. So to encrypt a message, the message is encrypted under the joint public key. Evaluations are done under this common key. And to decrypt a message, a minimum number of users, the threshold, must collaborate. An easy way to see that is in the k out of k threshold, where the joint public key is just the sum of all the individual public keys, and the joint secret key is the sum of all the individual secret keys. And to decrypt a message, each user will just partially decrypt it with her own secret key and broadcast the results. Then all the different partial decryptions are combined to get the final result. And why is CPAD a natural context for threshold FHE? Because in threshold, a user can just pick a message M, encrypt it under the joint public key, ask the server to evaluate a function on it, and then ask all the other users to collaborate to decrypt the result. Because a user has access to ciphertext and decryptions, and their decryptions, the user has access to a decryption oracle, well, to a CPAD decryption oracle. So any decrypting party in a threshold FHE setup is in the position of a CPAD attacker and may therefore recover the joint secret key. So the question now is whether our attack works against threshold FHE. And the answer is, in fact, no. No, because here we have the collaborative key switch decryption algorithm of Latigo. And as we can see in it, well, each user add a smudging noise to their ciphertext. So they flood their ciphertext during the partial decryption, and it is this flooded ciphertext that is eventually decrypted. This technique is called smudging or flooding, and it ensures that, I will try to say it in one shot, the distribution of the input ciphertext plus the smudging noise is statistically indistinguishable from the distribution of the smudging noise alone. I have said it. So that we can extract, sorry, it was too good to be true. So that we can extract no information on the noise. And so that's a natural countermeasure against our attack. Well, as I said, too good to be true. Well, this countermeasure have a cost because it requires larger parameters. And as no effective attack was known so far, the implementations of smudging for some libraries such as Latigo or OpenFHE, well, was not correct, as they used a smudging noise that was not large enough. And so our attack works against these implementations even when the recommended smudging noise, but not large enough because it was not lambda and sigma city dependent, was used. So as a takeaway, threshold FHE is not subject to our attack, provided that libraries correctly implement smudging. Okay, and so I still have a little time to talk about countermeasures. So we just listed three countermeasures against our attack. They aim to ensure that an attacker have a probability neg lambda to observe an exploitable decryption error. And so they are not optimal, but just sufficient to prevent our type of attacks. The idea behind the first one is quite simple. As our type of attacks does not work on correct schemes, we should make the FHE schemes correct. And one way to guarantee this is to bootstrap after each homomorphic operations, including additions. Just a word about bootstrapping, because nowadays the bootstrapping error is seen as a reliability issue and not a security one, but we should see it as a security one, and so parameters should be modified to have a neg lambda probability of error. And the two other countermeasures are the monitor and block technique that refuses to decrypt when the noise deviation is too large, and the monitor and smudge that embeds flooding into the decryption process, as in threshold. Right before the conclusion, I would just like to say that it has been a busy year on the topic of CPAD security for FHE, with many works and other lines of attacks being proposed, and also security notions being defined. So all these works open many interesting questions on this topic, so you should all stay tuned for further development on CPAD security for FHE. And so we're reaching the end of this presentation. So let me just give you a few takeaways. First, you should now all be convinced that CPAD security is a real threat, and that all FHE practitioners should take CPAD into account, whatever the scheme they use. Second, we just saw that simple CPAD attacks can be implemented, but we also have shown that countermeasures may be devised, though they have a cost. And as a last advice, I want to recall you to implement smudging appropriately in your favorite threshold FHE schemes if you want to avoid the threat of a CPAD attacker. Thank you very much for your kind attention.
Do we have any questions from the audience? All right, please come down to a microphone. Try turning it
on. Thank you for your talk. Just want to know if you have asked any or discussed the countermeasures with other libraries, and what's their take on the countermeasure?
Sorry, you wanted me to talk about the countermeasures, that's right?
Yeah. Just wonder, if you have discussed with the other the mainstream libraries?
The question is about other libraries, if they...
I have not discussed directly with other libraries, but some have, like OpenFHE, have improved their ePrint. So we know that they aim to implement some countermeasures for CPD attacks in a further work. And I can say that, well, no, it's not this way. Okay, no, I will be there. Okay, thanks. For example, for the monitor and block technique, many libraries implement the monitoring, but just they don't block the decryption, so we can still implement the attack, and we can still observe decryption errors. And so I think that they should just say that we cannot have the decryption, because otherwise, well, as you can see, we can implement the attack. And about the bootstrapping, well, it's more like a TFHE fuse-style crypto system. It's more for TFHE fuse-style crypto systems, but we just have to be careful about the bootstrapping error. And for the last one, the monitor and smudge, well, you know now that we must implement it for threshold schemes. We can also do it for single party scheme, well, when we have a single user, but we see that the cost is, well, it's most costly than the monitor and block, so I'll suggest more to use the monitor and block. I hope it answers to the question.
Yeah, thank you.
All right, let's thank our speaker again. All right, our next talk of the session is going to be how to construct quantum FHE generically, and Aparna will give the talk.
Hi, everyone. I'll be talking about joint work with my advisor, Vinod Vaikuntanathan, on how to construct quantum FHE generically. So let me first quickly recall the setup for classical FHE. We have a computationally weak client who wants to use a server's resources to compute some expensive circuit on its input X. And the constraint is that the server should not learn anything about X. What FHE allows you to do is the client can encrypt X as a ciphertext and send C along with some evaluation key to the server. The server can then use this evaluation key to compute C on X homomorphically under the encryption, so that when the client finally decrypts this output, it gets back C of X. And of course, we want the client to be efficient. That is, the decryption should be more efficient than computing C itself. Okay, so fast forward a decade or two into the future. So Google and IBM have quantum computers now. And the client might want to outsource quantum computation to Google or IBM servers. The only thing that changes here is that the server is now quantum. And so we want to expand the functionality to allow homomorphic encryption, homomorphic evaluation of even quantum circuits. And again, ideally, we want the client to be efficient so that decryption is more efficient than computing Q itself. But also, we want to enforce that everything that the client does, key generation, encryption, and decryption should be classical. So what was known about quantum FHE in the past? The first schemes by Broadbent and Jeffrey, and then Dulac, Schaffner, and Spielman constructed quantum FHE, except they needed the client to be quantum. But given a quantum client with unlimited quantum power, they were able to transform almost any post-quantum classical FHE into a quantum FHE scheme. I say almost because there is this one caveat that also shows up later, where the classical FHE scheme needed to have a low-depth decryption circuit. Okay, but in 2018, Mahadev's breakthrough result and follow-up work by Brzezinski constructed QFHE for classical clients. But now they needed much more specialized assumptions. They needed learning with errors. And if you look at their constructions, they rely very intricately on special structural properties of LWE that are going to be very hard to find elsewhere in other crypto assumptions. So the question we're interested in is this trade-off inherent, or can we get the best of both worlds? Concretely, does classical client QFHE really need learning with errors? Why do we care? Well, first, what if our worst nightmares come true and somehow we manage to break LWE? We don't want to put all our eggs in the same basket, and only earlier this year, there was an attempt at breaking LWE, and we can only expect more such attempts in the future. And secondly, we might want to have a couple of different constructions because each construction might have its own different efficiency profile and might be suitable for use in different contexts. So it would be really nice to have the following modular dream theorem that says that any post-quantum classical FHE scheme can be converted into a quantum FHE scheme. We don't quite get here, but we take a step in this direction. So we show that almost any post-quantum classical FHE scheme plus these dual mode trapdoor functions, and I'll define them later on in the talk, give you a quantum FHE construction. And you might have heard of trapdoor Clophy functions in like other quantum crypto schemes, and they're closely related to dual mode trapdoor functions. Okay, so this theorem is nice because of two reasons. One, it's modular and gives a construction of QFHE from generic crypto primitives. But two, it enables us to get other QFHE constructions. So for example, we know how to construct classical FHE from LWE, but we also know how to get it from post-quantum IO and re-randomizable encryption. By an observation of Wicks, we can get re-randomizable encryption from these so-called group action-based assumptions. And I won't get into more details about this, but it's like a framework for thinking about computational assumptions related to elliptic curve isogenies, which are also believed to be post-quantum secure. And on the other side, we already knew how to construct these dual mode trapdoor functions from LWE. But as a secondary result, we also show that we can get this primitive from the same group actions. And we do this by building on work of Alamati, Malavolta, and Rahimi, who build single mode trapdoor Clophy functions from the same assumptions. Already, this gives us a new construction of QFHE, namely from post-quantum IO and group actions. Okay, so for a minute, let's consider a slightly different setting where the client is no longer an iPhone, but it's a slightly more powerful classical computer. In this case, the definition is still meaningful if we allow the client computation to sort of grow with the size of the circuit, of the quantum circuit Q, and even allow more rounds of interaction. This is still a meaningful notion of outsourcing quantum computation. Recall in the classical setting, this is not helpful, this is not useful because the client could just like run the entire circuit on its own. But in the quantum setting, this is fine as long as we maintain that the client is completely classical. And indeed, this notion is called blind delegated computation in the literature, and previously the only constructions we knew needed learning with errors. So what do we achieve in the non-compact setting? We actually see that we don't need classical FHE in the non-compact setting. Just dual mode trapdoor functions suffice. And by our second result, this means that we get a new construction of non-compact QFHE from just group actions. It's interesting to note here that group actions are not known to imply classical compact FHE, but in the quantum setting, they allow us to realize this non-compact version. Okay, so for the rest of the talk, let's go back to the compact version, and I'll try to give a high-level overview of how our scheme works. The starting point is this really nice work by Dulac, Schaffner, and Spielman. Recall that their client needed to be quantum. Why is that? Even though the encryption and decryption procedures were totally classical, the key generation had to be quantum because the client had to prepare these quantum evaluation keys to send to the server so that the server could carry out this evaluation algorithm. And the client needed to do this because the evaluation keys depended on the secret key, and revealing the secret key would sort of break the semantic security. Okay, so our main conceptual idea is to get around this issue by using the notion of remote state preparation, where the goal is to replace quantum communication with classical communication. So at a very high level, and I'm going to gloss over a lot of details, say we have a family of states indexed by this index set I, and as part of some protocol, the client needs to pick one of these states and send it to the server. The goal of RSP is to replace this quantum communication and instead have the client send classical instructions to prepare the state in a way that hides which state you're asking to prepare. And so now the server can prepare the state on its own. What is known about RSP in the past? This is not exactly how these results are stated, but they basically give you remote state preparation, or RSP, for this certain family of states called BB84 states, assuming dual mode trapdoor functions. All right, but we needed to RSP these evaluation keys from the DSS scheme. And our main technical contribution is to show that yes, indeed, assuming post-quantum dual mode trapdoor functions, we get an RSP protocol for these evaluation keys. So again, to reiterate our main idea, we take the DSS scheme, and instead of having the client prepare quantum evaluation keys to send to the server, it sends these classical instructions to the servers that allow the server to prepare its own evaluation key. And crucially, these instructions don't reveal anything about the secret key. And so now the server can prepare its own evaluation key and run the DSS homomorphic evaluation. And now we have a classical client. Okay, so let me tell you a bit more about how we prove this. Our first observation is that even though the DSS evaluation key is really complicated to describe, and I won't get into it, but it suffices to RSP like one of these two states. In the first state, each of these states are like 3-qubit states, and the first state has qubits 1 and 2 entangled, and the second state has qubits 1 and 3 entangled. And we show that we can get a remote state preparation for this family of states using dual mode trapdoor functions. I won't say anything about the proof of step 1, but I'll try to give some intuition for why dual mode trapdoor functions are useful in step 2. At this point, I should probably define what dual mode trapdoor functions are. So think of a pair of injective functions, f0 and f1, such that either they have the same image or they have completely disjoint images. And the security property requires that given keys to evaluate f0 and f1, it's hard to tell whether they're in mode 1 or in mode 2. Oh. Okay, and right, so the security property requires that we're not able to tell which mode a particular pair of functions is in. And we also want a trapdoor that allows efficient inversion in both these modes. And this primitive shows up a lot in quantum crypto protocols. So to see why they're useful, let's try to look at the remote state preparation protocol for BB84 states to get some intuition. What are BB84 states? They're a collection of 4 states, 4 single qubit states, where the first 2 states are singleton states, just the classical bits 0 and 1. And the second 2 states are uniform superpositions over 0 and 1. Except the fourth one has this like phase or minus sign on 1. Okay, so how do we RSP this state? The first step is to prepare a state over 2 registers. The first one is an equal superposition over bit B being either 0 or 1. And the second register is an equal superposition over all inputs in the domain of the function, in the domain of the chapter function. And so one thing you can do on a quantum computer is in a third register, compute in superposition the output of f sub b on x. The second step, you measure the third register. Let's say you get some output y. Suppose we were, okay, so when you get an output y, we sort of collapse to the values of b and x that are consistent with y. So only the values of b and x that remain are ones such that f sub b of x is equal to y. If we were in mode 1, then these 2 functions had the same image. So y would have a preimage under f0 and another preimage under f1. And so the state collapses to an equal superposition over these 2 preimages, so 0x0 plus 1x1. On the other hand, if we were in mode 2, where the functions had disjoint images, y would have a preimage only under one of these functions. And so we get a singleton state, either 0x0 or 1x1. And you can see we're almost done, except there's this extra x register hanging around. Turns out you can easily fix this via a standard procedure by measuring the second register in a Hadamard basis to get rid of the x's. So in mode 1, what would end up happening is finally you get a random state from either the third or fourth BB84 states, or in mode 2, you would get a random state from 1 or 2, the first 2 states. And since, because of the security property of the dual mode trapdoor functions, the server is not able to tell which case it's in. Okay, but that was for the simpler family of BB84 states. And recall to RSP this DSS evaluation keys, we wanted to RSP this family of 3 qubit states, where either the first qubit is entangled to the second qubit or the third qubit. To be a bit more specific about what I mean by that, the first state has a uniform superposition over all 3-bit strings where the first and second bits are equal. And the second state is a uniform superposition over all 3-bit strings where the first and third bits are equal. Okay, so if the client wanted the server to prepare state 1, what the server wants to do is prepare this uniform superposition over all 8 possible 3-bit strings, and then collapse to the ones where the first and second bits are equal. So that is, we want to project to these blue strings. So how do we do this? We could try doing the same thing as before. So we have 2 registers. The first register now has 3 qubits because it's a 3-qubit state. And the second register is a uniform superposition over the input domain. And in the third register, instead of having 2 functions, now we have 8 functions, indexed because they're indexed by 3 bits, u, v, and w. And ideally, if we measure the third register, we want to sort of collapse to only the UVWs that are blue. And For this, we want to design these functions, these 8 functions, in a manner that the blue UVWs map to the same range y1, and the red UVWs map to a disjoint image y2. And so ideally, if we measured the third register, we'd want to get a uniform superposition over the blue states or the blue strings. But it turns out it's okay if we ended up in the complement, if we measured like a y2 output, because the red state is sort of like a single correction away from the blue state. And now we're basically done. Okay, so I guess we can construct this collection of 8 functions from dual mode trapdoor functions, the ones I defined earlier. And now we're done, because we can measure the second register in the Hadamard basis, like before, to get like a superposition over these blue strings. Okay, so to wrap up, let me give a quick summary of our results. First, we gave a theorem that showed a generic way to take any classical FHE scheme and a dual mode trapdoor function to give a quantum FHE scheme. And second, we showed that we can construct these dual mode trapdoor functions from group actions. These 2 theorems imply that post-quantum IO plus group actions give you a new quantum FHE scheme. In the non-compact setting, we
Excuse me, can you remove that from the screen? You have a pop-up. Thank you. Your spelling was correct on the slides, so it's very unjustified.
Right, so in the non-compact setting, we know that we need only dual mode trapdoor functions. And so theorem 2 gives us a new construction of non-compact QFHE from just group actions. Okay, I'll end with some open questions. First, is the dream theorem we started out with actually true? Can we convert any post-quantum classical FHE scheme into a quantum FHE scheme? And this would be the most aesthetically satisfying statement, but we don't quite get there. And second, in the non-compact setting, what are the minimal assumptions we need? As we saw, we don't need classical FHE. And by our work, only dual mode trapdoor functions suffice. But what is the minimal assumption? Are dual mode trapdoor functions necessary? So it turns out there is some evidence that information theoretic security is unlikely. But can you get them from, say, one-way functions? Yeah, that's my talk. Thank you.
Let's thank our speaker. We're running a little late on time, so please hold your questions in superposition until the next break. And if the final speaker could please come up. Thank you. Let's thank our speaker one more time.
Okay, how can I turn on? Okay.
All right, our final talk of the session will be plaintext ciphertext matrix multiplication and FHE bootstrapping fast and fused, and Jaehoon will give the talk.
Thank you. So hello, everyone. I'm Jaehyun Park from Seoul National University, and I'll be talking about plaintext ciphertext matrix multiplication and FHE bootstrapping, which is fast and fused. So this is a joint work with Youngjin Bae, Jung-Hee Chun, Guillaume Lo, and Damian Stelle. So here's a brief summary of this talk. So we suggest several fast methods for plain text ciphertext matrix multiplication. In this talk, we will say PCMM. And our evaluation takes like 0.3 seconds for PCMM for multiplying two matrices of like dimension 256 in a single thread CPU. And this is a like huge improvement compared to the existing work. And we made this improvement by using a reduction from PCMM to clear text, plain text matrix multiplications. And second, we also suggest a batch bootstrapping with higher throughput for ring RWA-based homomorphic encryption schemes. And if there are like 32 batch ciphertext, then we can achieve a like twice higher throughput compared to the conventional bootstrapping. And finally, we fused PCMM with the batch bootstrapping, and our batch bootstrapping with PCMM achieved like 41% faster than the current bootstrapping without PCMM. Okay, so matrix multiplication is central in high performance computation, especially for like large language models or large machine learning tasks. And as it is important, there exists like several highly optimized libraries for clear text matrix multiplication, which we call BLAST libraries. And they are really like highly optimized. They like optimize the memory access pattern and all kind of the things. So compared to my C naive implementation of schoolbook algorithm of matrix multiplication, in our machine, it was like 10 times faster. So that means like if we can use BLAST libraries, that will improve the efficiency by a lot. And our question was like, so, okay, we have like fast libraries for clear matrix multiplication, but what about matrix multiplication over encrypted data? So this is interesting if we think of some privacy preserving machine learning scenarios. So for example, this is a typical example of privacy preserving machine learning based on homomorphic encryption. So a client send a encrypted query to a server, and server evaluate the machine learning model over the encrypted query and send the encrypted result back to the client. So to do this, the client server should be able to evaluate the machine learning model over encrypted data. And during that, it often like faced to several kinds of matrix multiplication like this. So some of them are multiplication between like two plaintext matrices, which we call PPMM. And some of them are like multiplication between like encrypted and unencrypted matrices, which we call PCMM. And some of them are that between like encrypted ones, which we call CCMM. So in this talk, we will focus on PCMM. And I want to mention that like when we are considering like large language models, then like various dimensional PCMM and CCMMs appears in diverse steps. So for example, when you go to GPT, then we should, at some stage, we should address PCMM of dimension like from 128 to like more than 16,000. So in this work, we focus on the plain text ciphertext matrix multiplications. So we are given a plain text matrix U and encrypted matrix V, and our goal is to obtain the encryption of the product matrix UV. So for the ease of discussion, we will focus on the square matrices, and when we say divide D PCMM, that means like the dimension of the matrices are D. And also in this work and in this talk, we mostly focus on PCMM with ring RWA-based FHE schemes. So the reason why we focus on FHE schemes are we want to use it for privacy preserving machine learning or other tasks. So we want it to compatible with other machine learning tasks. And the reason why we focus on ring RWA-based schemes are we want some like high efficiency in terms of throughput. And in particular, in this work, we perform PCMM with CKKS scheme. Okay, when we do PCMM with CKKS, so let's see what happened. And before delving into detail, I want to briefly introduce what CKKS is. So in CKKS, we encrypt a vector of real numbers. So there are like several numbers in a single ciphertext. And a native operation supported by CKKS are component-wise parallel addition and multiplication and rotations, which rotate the vector inside the ciphertext. Okay, so when we try to implement PCMM with CKKS, it sometimes requires like several ciphertexts to store large matrices. And also like with native operations, PCMM usually requires lots of rotations. So this is problematic, actually. So for example, like a notable work from Jiang et al. Has a good bit complexity asymptotically, but it is compared to the clear matrix multiplication with BLAST libraries, it is order of magnitude slower. And we found that like the main reason of that is the loss of rotations. So rotation itself is heavy, but and more importantly, like it is not very compatible with BLAST libraries, so it makes it difficult to use BLAST libraries for PCMM. So our question is how to utilize BLAST libraries for PCMM. And the second interesting question was like how to manage those like multiple ciphertexts involved in large PCMMs. So to address the first issue, we suggest a reduction from PCMM to PPMMs. And to tackle the second one, we suggest a batch ciphertext computation. Okay, let's start with the reduction from PCMM to PPMM. So 2 years ago, Liu et al. Considered a verifiable PCMM, so they want to verify PCMM. And their idea was they reduce one PCMM to 2 PPMMs, and they verify PCMM by using 2 PPMMs. So here's the diagrams. And their restriction was like they can only verify the large matrices. So the dimension of matrix should be like larger or equal to the ring degree of the underlying ring algebra scheme. And we observed that this is a great idea for fast PCMM. So as they mentioned, one PCMM can be done by 2 PPMMs, and for PPMMs, we can fully utilize the high efficiency of existing BLAST libraries. So this is a great idea for PCMM. So let's look a bit more detail about the reduction. Okay, so in CKK scheme, we usually consider some cyclotomic ring like this, and a ciphertext has a form of A, B, where B equals AS plus M. So S is the secret key, and M is the encoded message. And you can simply like check the entry to see that this ring relation is equivalent to the following linear equation. So there is a structure in the S part. So the and AI and BI and MI are the coefficients of A and B and S and M respectively. So here you can see the structured linear equation. So this is equivalence, which means like if you have a ring algebra ciphertext, then you can write it as this linear equation. And conversely, if you have a linear equation like this, then you can construct a ring algebra ciphertext from this. Okay. And if you have like multiple ciphertexts with a shared secret, then you can stack this linear equation vertically to achieve something like this. So here, so this means that like if you want to encrypt a matrix, then you can stack this vertically, and that is related to a structured matrix equation. So this is our key observation. So yeah, so this is the start point of the reduction. And from this, suppose we have a row-wise encryption of matrix V. So that means we are given a linear equation like this. And once we multiply a plain text matrix on both sides, it turns out to be another structured matrix like this. So as I mentioned before, this is equivalent to the N-ring algebra ciphertext related to encrypting the product matrix UV. So this means that we have computed the PCMM, and we complete the PCMM task. So this means that we can do PCMM by using 2 PPMM, UA and UV. So that means we can utilize the high efficiency of existing BLAST libraries, and this will improve the latency and efficiency by a lot. Okay, so this is good. But here the limitation is that the matrix size is limited, so they are really large matrices. Okay, so then what happens if the matrices are like small or large? So for small matrices, at the first glance, it is like unclear how to reduce it to PPMMs, because like it requires some rotations and some data movements across loads within ciphertext. And actually those kind of rotations are related to key switching of homomorphic encryption, and that is not very compatible with BLAST libraries. So it's unclear how to reduce it to PPMMs. And for large matrices, we can indeed reduce it to 2 PPMMs, but the latency of 2 ppms might not be that satisfactory. So we would just wonder if we can do better than 2 ppms or not. So we solve these issues by using different formats of ciphertext. So precisely, we use module LW and multi-secret ring LW schemes, ring LW formats. So for small matrices, we use module LW ciphertext. So here, as I mentioned, the ring LW-based PCMM was like difficult to reduce to be PPMM. So instead of doing that, we convert it to the module LW ciphertext, and we perform PCMM over the module LW ciphertext. And this can be easily reduced to PPMMs. And for the large matrices, we do the same thing with the multi-secret ring LW. So here, then, we additionally require some convergence. So for the conversion between ring LW and module LW, there are several works. So for example, last year crypto, there's a paper Hermes from our group. And for the multi-secret ring LW conversion, we propose some algorithms for that in this paper. Okay, so I want to mention that the format conversions are relatively minor compared to the PCMM task itself. So in the rest of time, in the rest of the talk, with the limited time, I want to focus on the large matrix case and how to reduce the multi-secret ring LW PCMM to PPMMs. Okay, so for large matrices, we're going to use multi-secret ring LW. So in that case, the multi-secret ring LW ciphertext share the A part rather than the secret. So in that case, as we did for the ring LW, we can simply verify the entry to see that multi-secret ring LW ciphertexts are equivalent to a structured linear equation, but with some different structures here. So this is the structure for the multi-secret ring LW. And if we have a bundle of multi-secret ring LW ciphertext, then we can stack it vertically as before. And this means that for the large matrices, we can use multi-secret ring LW ciphertext to encrypt them, and that is equivalent to the structure matrix equation like this. Okay, so from that observation, we can make reduction again. So we are given the encryption of large matrix V, and once we multiply a plaintext matrix U on the both sides, then it turns out to be another structure matrix equation, which is related to a bundle of multi-secret ring LW ciphertext. So that means that multi-secret ring LW PCMM can be reduced to 2 PPMMs, UA and UV. And this is a reduction, and I want to highlight that as the size of A is much smaller than the size of V, PPMM UA is much easier than PPMM UV. So this means that with the multi-secret ring LW, PCMM can be done easier than 2 PPMMs with the same size. Okay, so here are some evaluations. So in the paper, we have several versions of algorithms, and for the precision optimized one, or PCMM was like slower than the PPMM by only factor of 6.3 or less. So this is not slower by orders of magnitudes, just like six times slower. And for the latency optimized one, it was like faster and slower by a factor of like less than 3.5. So it was good. And also we address another interesting question, how to manage like multiple ciphertexts. And so like if there are like multiple ciphertexts, like conventionally, like we compute the ring LW ciphertext one by one, but we can use multi-secret ring LW to make it faster. So we first convert them to share the A part, and we can, with the multi-secret ring LW with the shared A part, we can share the computation on the A part. And usually for the homomorphic operations, the computation on A part is much heavier than the B part, so this can save the time a lot. So with this kind of strategy, we can batch several homomorphic operations. So we can batch component-wide addition and plaintext ciphertext multiplication and rotations. But currently, we don't have a good idea for the ciphertext multiplication. But it already is very interesting because we can make a batch FH bootstrapping with this. So during CKGS bootstrapping, there are C2S and S2C, which do not require ciphertext multiplication. So we can batch C2S and S2C by using this strategy. So with that, we make an evaluation. So if there are like 32 batches, then or the batch bootstrapping has like twice higher throughput compared to the existing bootstrapping. And finally, we can fuse PCMM and batch bootstrapping, and compared to the current bootstrapping without PCMM mode for large matrices, or fuse bootstrapping with PCMM was like faster by 41%. So let me wrap up. So we suggest fast methods for PCMM, and we address like various dimensional matrices by using various formats of ciphertext. And we exploit BLAST libraries to do that. And our PCMM is like only like less than 3.5% slower for large matrices. And also, this is not included in the talk, but in the paper, we also suggest even faster PCMM with the fixed plaintext matrix case. And also, we suggest some conversion algorithms from ring LWE to multi-sig ring LWE. So we refer to the paper for the details. And we also suggest a batch FH bootstrapping, and it was fast. So your paper are available online, so thank you for listening.
All right, let's thank all the speakers in the session one more time. Thank you. We are on coffee break now, and sessions will resume at 10:50.